In our previous lecture, we solved a few problems on the second law of thermodynamics quantified in terms of entropy and entropy generation for a control mass system. So, we will continue with the problem solving. The next problem is problem 6.4. A rigid container with a volume of 200 liter is divided into two equal volumes by a partition. So, A and B both have nitrogen, one side 2 MPa 200 degree centigrade, let us say side A, and other side 200 kPa 100 degree centigrade. The partition ruptures and the nitrogen comes to a uniform state of 70 degree centigrade. Assuming the temperature of the surroundings to be 20 degree centigrade, determine the work done and the net entropy change during the process. So, let us work out this problem in the board. We will draw a schematic of the problem as per our regular custom, and then we will solve. So, we will assume here nitrogen as ideal gas. This is an assumption. So, state A1, V is 100 liter, because total volume is 200 liter, it is divided into two parts. Pressure is 2 megapascal, sorry 200 degree centigrade, not 20, 200 degree centigrade. So, 473.15 Kelvin. State B1, VB1 100 liter, PB1 2 MPa 200 kPa, TB1 100 degree centigrade, that is 373.15 Kelvin. So, what is the final pressure? Let us say it is one of the primary things that we will calculate. It is not given as a part of the question that find out the final pressure. Why do you require the final pressure? You require the final pressure because to calculate the change in entropy, entropy change for an ideal gas is a function of both pressure change and temperature change. So, final pressure will be required. So, how do you calculate the final pressure? So, when this is ruptured, A plus B will become the total thing in the chamber. It will have a common pressure and common temperature till it comes to when it comes to equilibrium. So, P2 into Va plus Vb, that is the total volume, is equal to M total R T2, right. M total is nothing but Ma1 plus Mb1, because total mass does not change, it is just a redistribution of mass, but A plus B whatever is the mass within the chamber that does not change. So, how do you get Ma1 and Mb1? You know Pa1 Va1 is equal to Ma1 R T1. So, this will give you what is Ma1, because all other things are known. Similarly, Pb1 Vb1 is equal to Mb1 R T1. So, this will give you what is Mb1. So, this R is R of nitrogen, as I told that when you consider the mass basis, this R is not the universal constant, it is universal constant divided by molecular weight. So, for nitrogen the value of R will be 0.2968 kilojoule per kg Kelvin, and Cp of nitrogen, which we will require for one part of the problem, is 1.042 kilojoule per kg Kelvin. Once you have R and Cp, you can calculate Cv, that does not require additional input because Cp minus Cv is R. So, once you have this Ma1 and Mb1, you can calculate P2 from here. This is Va plus Vb is 200 liter, right. So, you now have P2. So, then what is asked, first part is what is the work done. This is the easiest part, because when this is ruptured there is a redistribution of A and B, but overall there is no movement of the system boundary. So, work done is 0. So, work done is 0 for the system, for system A plus B. Okay. Now, you apply first law. So, what we have to find out is the entropy generation. So, entropy generation calculation will require two steps. The first step is you calculate the heat transfer, and based on the heat transfer you put it in the expression for entropy change to get the entropy generation. How do you calculate the heat transfer? For that you require the first law of thermodynamics. So, first law Q12 is equal to U2 minus U1 plus W12. U2 minus U1 is U2 minus U1 of A plus U2 minus U1 of B. So, Ma1 Cv into T2 minus Ta1 plus Mb1 Cv into T2 minus Tb1, assuming constant Cv. So, if you do that, and final temperature, what is the final temperature is 70 degrees centigrade. So, state 2 you have 70 degrees centigrade, and pressure also you have found out. Here pressure is not required, because the internal energy of an ideal gas is a function of temperature only. So, you substitute all these values and you can get what is the heat transfer. So, this is minus 141.95 kilojoule. Okay. So, then what you require is the entropy generation. So, for that we will apply the entropy change formula. So, S2 minus S1 so if you substitute here temperature of the surroundings, this will include the total entropy generation, that includes the heat transfer from the surrounding to the system or system to the surrounding in this case, because it is a negative heat transfer. So, S2 minus S1 is S2 minus S1 of A plus S2 minus S1 of B. S2 minus S1 of A is MA1 CV, or we can use Cp or Cv depending on whether we are calculating it on a volume basis or pressure basis. So, if we are calculating it on a volume basis pressure basis, then Cp1 or Cp into ln T2 by Ta1 minus R ln P2 by Pa1 plus Mb1 Cp ln T2 by Tb1 minus R ln P2 by Pb1, right. So, you can calculate the value, the T0 is given to be 20 degree centigrade. So, this is 293.15 Kelvin, this you already know, here you can substitute the values. So, you will get entropy generation. Entropy generation is 0.2947 kilojoule per Kelvin. Okay. So, we will move on to the next problem. Let me erase the board before we move on to the next problem. Next is problem number 6.5. You have 1 kg of ammonia contained in a spring loaded piston. The state 1 is saturated liquid at minus 20 degree centigrade. Heat is added from a reservoir at 100 degree centigrade until a final condition of 800 kPa 70 degree centigrade is reached. Find the work, heat transfer and entropy generation assuming the process is internally reversible. Okay. So, you have ammonia M is equal to 1 kg. This is our system. State 1, T1 is equal to minus 20 degree centigrade, x1 is equal to 1. So, what other properties we will require, I will come to that when we solve, but let us first identify the states 1 and 2. State 2 is T2 is 70 degree centigrade, P2 is 800 kilopascal. The first thing that we will require, like when heat is transferred from this T0 to here, there will be an expansion. So, there will be a work done. If it is internally reversible, that means it will move in a quasi equilibrium process. So, work done will be integral PdV. Quasi equilibrium we can write it. So, this will be, so pressure versus volume will be linear because the spring that is resisting is linear. So, the work done, we have done such problems so many times that I can straight away write the expression for the work done. So, integral P dV for linear pressure volume diagram will be half P1 plus P2 into V2 minus V1. So, how do you know this V2 minus V1? So, this means you know what is V1, which is nothing but sorry, this is saturated liquid, not saturated vapor, right. So, this is right. So, x1 is equal to 0. So, V1 is Vf1 at minus 20 degree centigrade. M is equal to or capital V1 is M into V1. So, this is the mass. In this case for state 2 you can calculate V2 from this T to P2, it will be definitely superheated vapor state. So, V2 will be equal to mV2. What is P1? P1 is P sat of at minus 20 degree centigrade. So, you know all these values, this will give you what is the work done, that is 97.768 kilojoule. Then once you know the work done, you can calculate the heat transfer. Q12 is equal to M into U2 minus U1 plus W12. So, you can also calculate U1, U1 is UF1 and U2 is from V2, this is from table of ammonia, and U2 also from table. So, M you know, U2 minus U1 you know, W12 you already know. So, from here you can find out what is Q12. So, Q12 is 1447.3 kilojoule. In most of the cases I am giving you answers of the intermediate steps with a hope that you know it will help you to check your calculations in between and allow you to have more confidence in problem solving with data taken from thermodynamic tables. And then you can apply the second law, M into S2 minus S1 is equal to Q12 by T0 plus Sgen. So, T0 is given 100 degree centigrade, right, that means 373.15 Kelvin. So, this will give you what is entropy generation, because everything else is known, is 1.307 kilojoule per Kelvin. So, this is a very straightforward exercise. We will move on to the next problem. Let
you have drawn the controlled mass, it should be the temperature at the system boundary, right?
Now, see, this is very important. So, you are asked to calculate what is the entropy generation during the process. So, when it is entropy generation during the process, it includes the sources of irreversibility both internal and external. Had it been entropy generation during the process within the system, then T would be the temperature of the system boundary. But when it includes this heat transfer as well, the temperature should be this one. So, this includes both internal and external irreversibility. Okay. So, let us erase this one before we move on to the next problems. We will solve a couple of problems more. So, the next problem, (6.6). You have two rigid tanks, each contain 10 kg of nitrogen at 1000 Kelvin at 500 kPa. So, they are connected by a reversible heat pump which heats the tank B and cools the tank A. So, it effectively transfers heat from a colder tank to a hotter tank, and that can be possible only by a work input. You have to find out the final pressure and temperature in both tanks and the work input to the heat pump, assuming constant heat capacities, and this process, all the processes are considered to be reversible. Okay. So, let me draw the schematic. So, you have A, so this is heated, let us say it goes from state 1 to state 2. This is cooled, let us say this goes from state 1 to state 3. So, now you can write, so T1 is 1000 Kelvin, this is given, whatever is given I am writing, T2 is 1500 Kelvin, T3 we do not know. Okay. So, then because this entire process is reversible, we can write delta S is equal to Q12 by T0 plus entropy generation, right. So, this delta S is the change in entropy of the nitrogen in A plus the change in entropy of nitrogen in B. There is no change in entropy for the heat pump because it is a cyclic process, it comes back to the same state. Heat transfer, if you consider this entire thing as a system, there is no external heat transfer, this you have to understand very carefully. This heat transfer is internal within the system, here the system is A plus heat pump plus B. Okay. So, then this is 0, and because the heat pump is functioning reversibly, all the heat transfers and changes of state are reversible, and therefore, the entropy generation is 0. So, the change in entropy is 0. So, S3 minus S1 of A plus S2 minus S1 of B, that is equal to 0. So, this is CV ln T3 by T1. I can write in addition plus R ln V3 by V1. So, this is 0 because there is no change in volume of this, plus so the mass each contain 10 kg. So, if this is M, this is also M, M is 10 kg. Similarly, CV ln T2 by T1 plus R ln V2 by V1. Okay. So, you can from here get ln T3 T2 by T1 square is equal to 0, that means T3 T2 equal to T1 square. So, you have T3 is equal to T1 square by T2, right. So, this will be 667 Kelvin, all right. Once this is 667 Kelvin, you can now use the ideal gas law, P3 by T3 is equal to P1 by T1. Actually P3 V3 by T3 is equal to P1 V1 by T1, V1 and V3 are the same. So, if you want I can write that and cancel if it helps you. So, you can find out from here what is P3. P1 is known, right. P1 is 500 kPa, 500 kPa. So, this will give you what is P3. This is 333 kPa. This is similarly P2 by T2 is equal to P1 by T1 again. So, here also you will get same way, P2 is 750 kPa. Now, you to get this work done you require heat transfer here and heat transfer here. So, for that you have to apply first law separately for A and B to get these heat transfers. Otherwise, if you apply first law for the whole system you will not get that. So, first law for A. So, Q12 is equal to or Q13 M into U3 minus U1 plus W13, W13 is 0. So, U3 minus U1 is equal to MCV into T3 minus T1, right. M is 10 kg. So, this will be I do not have a separate answer for this, but whatever Q13 comes out that is equal to minus QA, right, that much we can say. Why minus QA? Because the QA direction in the figure is shown to be heat transfer from A and Q13 positive by definition heat transfer to A, not from A. So, and we can apply the first law for B, Q12 is equal to M into U2 minus U1 plus W12. Okay. So, this is MCV into T2 minus T1. So, this is equal to QB, right. Now, what is the work done? So, from energy balance of the heat pump, if you apply the first law for the heat pump, you have QA plus W is equal to QB. So, W is equal to QB minus QA, which you get from these two, and that will be 1244 kilojoule. There is a final problem for this particular part of the chapter, and that problem I will not solve fully, but I will give you a hint how to solve, that is problem number 6.7. So, let me erase the board. I will not draw the picture completely, but I will give you some hint. At least one or two problems you should try by yourself with little bit of hint, and I will of course give you the final answer. So, let us look into the problem. A cylinder fitted with a frictionless piston contains water. A constant hydraulic pressure maintains the cylinder pressure at 10 MPa. So, the process is a constant pressure process. Constant pressure process, initially the water is 700 degree centigrade and volume is 100 liter, and then heat is transferred from the water. So, it is cooled and the piston will come down, its volume will come down. This heat is transferred to a heat engine and the heat engine rejects heat QL to the ambient, and in the process it does some work. If the entire process is reversible, find the net work output. So, this problem is very much similar to the previous problem, only difference is previous problem the tank was rigid, here instead of that there is a cylinder with a flexible with a moving boundary. So, in this case I will just give you a hint of how to solve the problem. So, you have the cylinder as the system first. So, you have Q12 is equal to m into U2 minus U1 plus W12. W12 is integral P dV, right. It is a constant pressure process. So, this is P into V2 minus V1. So, this you can write P2 V2 minus P1 V1 because P2 and P1 are the same. So, this is m P2 small v2 minus m P1 small v1. So, if you combine U2 with P2 V2, it is m into H2, similarly H1. So, by looking into the property tables, state 1 and state 2 you can get the enthalpy and then you will get m. So, state 1 is 700 degree centigrade 10 MPa, it is defined by that. State 2 10 MPa and it is condensed to saturated liquid 10 MPa and quality equal to 0, that is state 2. So, if you calculate this heat transfer, this is minus 5652.6 kilojoule. This is equal to minus QH because heat transfer to the cylinder is positive. So, heat transfer from the cylinder is negative, and then to calculate the net entropy generation you appeal to the second law, but second law applied to the cylinder plus the heat engine. So, second law you apply for the system water plus heat engine together. This is very important because the overall process is said to be reversible. So, S2 minus S1 is equal to Q12 by T0 plus entropy generation, right. Q12 by T0. So, S2 minus S1 is S2 minus S1 of water, because for the heat engine, because the process is cyclic, there is no S2 minus S1. What is this Q12? If you take the water and the heat engine together, look at the figure of the problem. If you look at, yes, just look into this figure, water and heat engine, the QH is internal, it is like action reaction force in free body diagram. So, water and heat engine together, the net heat transfer is minus QL, right. Water and heat engine together, net heat transfer is minus QL, and T0 is temperature of the ambient air, which is 30 degree centigrade, that is 273.15 plus 30 Kelvin. Entropy generation is 0 because the overall process is reversible. So, from here you can find out what is QL, right, and then you apply the first law for the heat engine to calculate the work done. So, W net is equal to QH minus QL. this is for this problem 3002 kilojoule. Okay. So, with this we have solved quite a few problems on the understanding of entropy change and entropy generation for a control mass system. How do these considerations change if it is a control volume instead of control mass system, that we will take up in the next lecture. Thank you.